Okay, so here's a number that should make your jaw drop. Almost every advanced chip in your phone, your laptop, the GPU running your favorite game, the data center training the AI you talked to this morning, pretty much all of it gets made on machines from a single company in the Netherlands called ASML. One company, and there is no plan B. And for years, that's been the most unshakable monopoly in all of technology. So, when I tell you that a tiny startup in California, backed by a former Intel CEO and a pile of US government money, thinks it has found a better way to make light for those machines, yeah, I set up too. Let me walk you through what's exactly happening here, because this is one of the coolest stories in tech right now, and I don't think enough people are talking about it. Okay, let's get on to the same page first. To carve transistors onto a chip, you need light. Really specific light. The smaller the wavelength, the smaller the feature you can print, and smaller features mean faster, more efficient chips. That's the whole game. ASML's flagship tool uses something called extreme ultraviolet light, or EUV, with a wavelength of 13.5 nanometers. To put that into perspective, that's hundreds of times smaller than visible light, and making that light is, frankly, insane. Now here's how they do it. They shoot tiny droplets of molten tin through a vacuum, and then they blast each droplet with one of the most powerful industrial lasers on the planet. The tin vaporizes into plasma, and that plasma spits out the UV light they need. They do this tens of thousands of times per second. I'm not exaggerating when I say that this might be the most complicated commercial process humans have ever pulled off, and it works. This is how we got 5 nanometer and 3 nanometer chips. The engineering is genuinely a miracle, and I want to be clear up front, nothing I'm about to say takes that away from it. But here's the thing about that tin vaporizing trick. It's running out of road. The whole method is called laser-produced plasma, or LPP, and it has some ugly problems baked in. First, it's wildly inefficient. We're talking roughly 1 to 1.5 megawatts of electricity going in, and you get a few hundred watts of usable EUV light on the other side. One researcher estimated that the actual conversion efficiency is under 1/10 of 1%. Most of that energy just becomes waste heat. That's not a rounding error. That's a whole design fighting you. Second, all that vaporized tin, it splatters. It coats the delicate, mind-bogglingly expensive mirrors inside the machine, so you're constantly fighting contamination. And third, and this is the big one, to push chips below 3 nanometer nodes, you need way more light power and shorter wavelengths than this approach can comfortably deliver. The tin droplet method is basically maxed out. ASML is squeezing it hard, working on a 1000-watt source that fires 3 lasers at 100,000 droplets a second, but even they know they're pushing against physics. So, the obvious question is, what if you made the light a completely different way? And that's where this gets fun. The challenger to LPP is a technology called a free electron laser, or FEL for short. And honestly, once you understand how it works, it's hard not to fall in love with it a little. Instead of vaporizing metal, you take electrons and accelerate them to the near speed of light using a particle accelerator. Then you send the beam screaming through something called an undulator, basically a long row of magnets with alternating poles. As the electrons weave back and forth through those magnets, they shed energy as light. And the magic part? By turning the electrons and the magnets, you can dial in almost any wavelength you want. That's the headline. It's tunable. Today's tin method is locked at 13.5 nanometers. Take it or leave it. A free electron laser can be tuned shorter, towards 6.x nanometers, into what people call beyond EUV. Shorter light, smaller transistors, more Moore's law. And there's no tin, so no contamination of those precious mirrors. But my favorite part is the efficiency story. A free electron laser laser is so powerful that a single one could feed light to as many as 10 to 20 lithography machines at once. Think about that. Right now, every ASML scanner needs its own light source bolted into it. With this approach, you build one central light plant and it powers an entire row of machines. One Japanese research design uses about 7 megawatts to produce 10 kilowatts of EUV, orders of magnitude better than the tin approach on the per watt basis. The whole economics of a chip factory could change. So, who's actually building this? The name to know is xLight, out of Palo Alto, California, and this is not some two guys in a garage situation. Their CEO and CTO, Nicholas Kellett, used to be the chief engineer of a 3-mile-long X-ray free electron laser at Stanford's SLAC lab. This is the guy who has actually built one of these monsters. Then, the part that made me do a double take is Pat Gelsinger, the former CEO of Intel, who joined xLight's board as executive chairman. Now, when the guy who ran Intel decides it's where the future is, I pay attention. They raised a 40 million Series B round, and then came the headline that really put them on the map. They signed a letter of intent with the US Department of Commerce for $150 million in proposed incentives under the CHIPS Act, and notably, this was the first award out of the Trump administration's new CHIPS Research Office. In exchange, the government would take an equity stake at the company. The US wants this technology built in American soil badly, because right now the most critical piece of the chip supply chain lives entirely overseas. The plan? Build the first full-scale free electron laser prototype at the Albany Nanotech Complex in New York, working with a non-profit called NY Creates, with the system up and running around 2028. xLight is even claiming their source could produce roughly 4 times the EUV power of today's best, boosting a factory productivity by 50% or more. Bold? Absolutely, but the pieces are real. And here's the detail I love, because it shows this isn't a fluke. xLight isn't alone. Over in Tsukuba, Japan, researchers at an organization called KEK, the High Energy Accelerator Research Organization, have been chipping away at this exact idea since 2015. Their design uses something called an energy recovery LINAC, which is a beautiful trick. After the electrons make the light, instead of just dumping that beam and wasting all of its energy, you send it back around and recover most of that energy to accelerate the next batch. It's recycling at the speed of light. They estimated they could build a system producing over 10 kilowatts of EUV for around $260 million, feeding multiple machines, with a free electron laser potentially being 10 to 100 times more efficient than the tin method. So this isn't one startup's wild bet. Serious accelerator physicists on 2 continents have independently looked at this and gone, yeah, this could actually work. And all of this begs the question, is ASML done for? Alright, time for me to be straight with you, because this is where the clickbait headlines and reality part ways, and the real story is honestly more interesting. No, ASML is not getting bulldozed next year. Here's the key thing that almost nobody mentions. xLight isn't trying to replace ASML's machines. It's trying to replace the light source inside them, the tin droplet bulb, not the camera. In fact, xLight literally says its goal is to enhance ASML's roadmap and plug its light into ASML's existing scanners. So, game over ASML is really game over for molten tin droplets. The scanner, the impossibly precise optics, and the stages that ASML spent decades perfecting, that's still very much the crown jewel. And here's my honest opinion and why I'm actually hooked rather than bearish on ASML. If this works, it could be the best thing to ever happen to chip making. Picture it. ASML's incredible machines but fed by a light source that's more powerful, more efficient, tunable to shorter wavelengths, and shared across a whole factory floor. That's not the death of EUV. That's EUV getting a turbocharger. Meanwhile, ASML keeps pushing its own roadmap with high NA and even hyper NA optics. The likely future isn't one winner crushing the other. It's these worlds merging, and we all get cheaper, faster chips out of it. And I'll take that deal every single time. Now, despite my enthusiasm, I'm an optimist, not a fanboy, so let's keep it real about the hurdles. A free electron laser is enormous. We're talking infrastructure that looks more like a national science facility than a piece of factory equipment. And that central light plant that's so efficient, it's also a single point of failure. If your one giant light source goes down, every machine it feeds goes dark at the same time. In a factory where an hour of downtime costs a fortune, this is a terrifying thought, and it's a real engineering and management problem to solve. Plus, the prototype isn't even due until 2028, and going from it works in a lab to it runs 24/7 in a factory without hiccups is a brutal years-long gauntlet. Loads of clever technologies have died right there in that phase, so I'm calibrating my excitement. This is a watch this closely over the next 5 years story, not a sell your ASML stock tomorrow story. But man, what a story it is. A particle accelerator, a tool we built to study the universe, getting repurposed to print the brains of every device we own. That's the kind of beautiful sideways innovation that reminds me why I love covering this stuff. And this is exactly why I wanted to make this for you, because we're early on this one. By the time it hits the mainstream headlines, you and I will already get it. So let me ask you straight up, do you think free electron lasers actually dethrone the tin droplet by 2030, or does ASML's own roadmap keep it ahead?